In this lecture, we shall be focusing on the two important properties that are related to DFT, namely the circular shift and the circular convolution. So before talking about these two specific properties which are pertaining to DFT, so let us first try to come up with a relation of DFT with Fourier series coefficient. So we saw that there are four variants of Fourier transform that exist pertaining to different types of signals. For example, if the signal is periodic and continuous, or it's discontinuous and periodic or aperiodic. So depending upon what type of signal that we are going to deal with, we have different types of Fourier transforms. And since we shall be talking about the DFTs and the two specific property which are only related to DFT, and that is why we shall be coming up with the relation of DFT with Fourier series coefficients, which will be useful in the properties that we are interested in. So this is the DFT of the signal sequence xn, and we had been learning about this transform given by xk, which is summation from n equal to 0 to n minus 1 xn e raised to power minus j2 pi kn upon capital N for k varied from 0 to n minus 1. So this is an n point sequence, and then we have a signal sequence xn. So this is in fact the relation that we obtain from the inverse discrete Fourier transform, or IDFT, or the synthesis equation. So these are the two equations that we had been studying in our previous lectures. And now if we talk about the periodic sequence, so suppose that we are given a periodic sequence xpn, and the Fourier series of sequence xpn, which has a fundamental period n, is given as xpn equal to summation k equal to 0 to n minus 1 ck e raised to power j2 pi nk divided by n. And this small n is varied from minus infinity to plus infinity. So this Fourier series accompanies the Fourier coefficient or the Fourier series coefficient, and that are given by the expression ck equal to 1 upon n summation n equal to 0 to n minus 1 xpn e raised to power minus j2 pi nk divided by n, where k is from 0 to n minus 1. So this is again an n point sequence. Now if we try to compare these equations with the equations of the DFT that we obtained, given in that are highlighted above at the top, so we see that this Fourier series coefficients, the sequence, are similar. So if you compare this particular equation with this one, so we have almost a very similar sequence, and thus we say that the xn is related to xp when n is defined for 0 to n minus 1. So there exists a relation between xn and xpn for this range of n. And the DFT of this sequence is thus given as xk, which is equal to n times ck. Since what we did is we equated these two values for this particular range of small n, and thus if we have this particular term xn equal to xpn, then in case of this equation given by xk, we have this term xn, and ck we have xpn, and since they are equal for this range, and thus the relation that exists between xk and ck will be n multiplied by xk equal to n multiplied by ck. So this can be confirmed from the relation, these two equations that are given. So the n point DFT provides the exact line spectrum of a periodic sequence with fundamental period n. So if you remember the Fourier series that you learned in your past, so we talked about the line and phase spectrum of ck. So there exists a line spectrum of ck, or in other terms amplitude versus frequency curve. So by this relation we conclude that the DFT with n points is the exact line spectrum of CK, or the periodic sequence with fundamental period n. Now if we talk about the DFT properties, so there are properties that are associated with DFTs, and much of these properties are similar to the properties of Fourier transform, Fourier series, and Z transform, like linearity, duality, multiplication, symmetry. Now there are two other properties which are specific to DFTs, which one of which is circular shift and the other is circular convolution. So the DFT has theorems and properties that are similar to those of the Fourier series, Fourier transform, and the Z transform. A major difference of the discrete Fourier transform is the implicit periodicity in both the time and frequency domains, that is circular shift and circular convolution. So we'll talk about these two properties in the upcoming slides, starting with circular shift. So the circular sequence shift, if suppose that we are given the relations of, again from the previous slide where we talked about the relation between the Fourier transform, the Fourier series, and the discrete Fourier transform. So we saw there that the xn is equal to a periodic signal xp for this particular range, and from this we have the endpoint DFT of a finite duration sequence xn of length L less than equal to n. So suppose that we are given a signal xn which has the duration less than or equal to n points, capital N. So this is equivalent to the endpoint DFT of the periodic signal sequence xpn of period n. So this is what we obtained in our previous slides. So in other words, periodically extending xn provides a sequence xpn. That is, xpn can be expressed in terms of xn by this relation where we have xn minus ln, capital N, summation where L varies from minus infinity to plus infinity. So what we did here is we obtained the periodic signal xpn from a signal xn by making it periodic from this expression. So which means that if you look into this expression, what we have this term capital N, which is the number of points present in the sequence x. So this x will be having number of points n, and in order that we repeat this signal xn from minus infinity to plus infinity, what we did is we shifted this xn by the term n and varied the multiplicative factor L from minus infinity to plus infinity. So what we are trying to do with this expression is we are trying to replicate the signal xn from minus infinity to plus infinity. So this will be clear by the upcoming question that will be shown in the upcoming slides. Now suppose that xpn is shifted by k units. So apart from this expression, this in fact also represents a shifted version of the signal xn, which are summed together. Now if we shift the signal xpn by k units, so what we get is, and the shifting is done towards right, so we obtain another periodic sequence which is given by xp dash of n. So this was a periodic sequence xpn, and now we obtain a shifted periodic sequence which is shifted by k units. So xp dash n is equal to xp n minus k, which is summation L from minus infinity to plus infinity xn minus k minus ln. So the same this sequence, which is again shifted by k units towards right. Thus the following finite duration sequence x dash n with n points is obtained. So we have a sequence x dash n. So we can now define, this is another definition of a finite duration sequence. So this is not infinite like xp dash n. So we can obtain from this xp dash n, which is in fact an infinite duration sequence, periodic in nature. So we define another sequence which is not of finite duration. In fact, it is the part of xp dash n cycle. So x dash n can be defined as xp dash n. So you don't have to worry about things like here. This will be clear in the upcoming question. So we are going to represent each of these things graphically, and thus it will make clear more. So suppose that we have a sequence x dash n, and this is given by xp dash n for the range where small n we talk about 0 to n minus 1. So again, so this is something related to xn, the original sequence, which had n points. So we now again obtain a sequence x dash n having n points, where n is from 0 to n minus 1, and that will be representing xp dash n, and for all other values of a small n, this will be 0. So now from the periodic sequence xp dash n, we obtained another sequence which is not periodic and is not defined for infinite duration. So this particular term that we have defined as x dash n is related to the original sequence xn by a property called circular shift, illustrated ahead. So this will be clear from the example now shown. So suppose that we are required to sketch x dash n, which is given by the signal xp n minus 3 for the given sequence. So in fact, what we are talking about, this xp n minus 3 is a periodic sequence, which is a sequence varying from minus infinity to plus infinity. But x dash n, so there is a slight correction here. This should in fact be written in this form. So we are talking about n point sequence for x dash n, and thus this should be an n point sequence. So since if we see the original curve xn, the value of capital N should be 8, because this sequence varies from 0 to n minus 1, where n minus 1 is 7, and thus capital N comes out to be 8. And thus this sequence x dash n will be plotted for xp n minus 3 when n is varied from 0 to 7, and this will be taken as 0 otherwise. So this question should be corrected, and it should be written, this term should be written in this manner, like x dash n equal to xp dash and 0 for these values. So I guess you all shall be correcting this. So now xn is given by this sequence, and we are required to eventually draw x dash n. So before this, we'll follow the relations that we obtained in the previous slides. So the first thing that we did was, so let us first redraw xn, the same sequence, and now we'll draw the sequence xpn. So xpn was obtained as summation L from minus infinity to plus infinity x n minus ln. Now we identified capital N as 8. So this will be 8L. So if you choose the value of a small l, L as 0, then what you get is x of n, the original sequence, when L is taken as 0. So for L equal to 0, xpn will be the same sequence copied just below it. So if we talk about this particular graph for xpn, then we'll be having the same sequence from 0 to 7 being copied here at this point for L equal to 0. When L is taken as 1, the same sequence is then shifted by 8 steps. So we'll be having the same sequence which will be copied ahead here. And if we talk about L minus 1, in that case the sequence will be shifted backward, and thus xpn will be a sequence that we will be obtaining from minus infinity to plus infinity, and it will be periodic in nature. So this is the sequence xpn, which is in fact periodic in nature, as well as it varies from minus infinity to plus infinity. The second step that we did was obtaining xp dash n, which was given by the shifted xp. So we now are trying to shift this by 8 steps. Sorry, 3 steps. So we will be shifting this sequence by 3 steps. and thus here this value of small k is 3, which means that the shifting will take place. So xpn will be shifted 3 steps ahead towards right. So now if we plot the shifted sequence, shifted by 3 steps of xpn, what we get is this sequence, which is xpn minus 3. Now finally, in order to obtain x dash n, so x dash n again will be defined for will be equal to xpn minus 3 for small n varied from 0 to 7. So we will be talking about this part only, while x dash n will be 0 for all other values of small n, and thus x dash n will be given by, since it is given by this expression xp dash for n between 0 to n minus 1, n minus 1 is 7 here, and thus we'll be interested in drawing the sequence xp dash n for 0 to 7, and we'll be taking it 0 otherwise, and thus what we get is this particular sequence. So this is x dash n and the final sequence that we were interested in. So if you have any problem or doubt related to circular sequence shift, you can post me questions or ask me, and we'll talk about the circular convolution in our next lecture.